Okay, in this example, we want to try to calculate the integral of this function here. It's 2x squared minus x minus 9 over x cubed minus 6x squared plus 9x. So, as usual, we first ask ourselves, well, can we immediately recognize the antiderivative of this function here? And the answer is almost certainly no. Next thing, we might like to try a u substitution. Most natural thing would probably be to let u equal the entire denominator here. Du, you can see, does not seem to show up in any obvious way in the numerator, so a simple substitution probably won't work. Doesn't appear to be a by parts type question. Maybe thinking about trig integrals, you could factor an x out of here. You'd be left with a quadratic in the denominator. You could maybe write that as a sum or difference of squares. Well, you could try that if you want, but you'll discover that that will likely be a nightmare. So what do? Well, you notice that, in fact, this is a rational function. So we have a polynomial, sum of powers of x in the numerator, over a polynomial in the denominator, sum of powers of x. We also notice that the degree of the numerator, which is 2, is strictly less than the degree of the denominator, which is 3. So, because we have a rational function with degree of the numerator strictly less than the degree of the denominator, we can immediately try to apply the method of partial fractions. If the degree of the numerator had been greater than or equal to the degree of the denominator, we would first divide the denominator into the numerator and then reassess. Okay, so if we're going to apply the method of partial fractions, the first thing that we want to do is factor the denominator. So let's just factor this denominator over here. We'll just do this off to the side. So we have x cubed minus 6x squared plus 9x. What's that equal to? Well, first of all, we can factor an x out of that. We'll be left with x squared minus 6x plus 9. And this is x times, check, x minus 3 all squared. Okay, so now what? Well, having factored the denominator, let's just rewrite this as 2x squared minus x minus 9 over x times x minus 3 all squared dx. Okay, so we factored the denominator. Now we can find a partial fraction decomposition of our function 2x squared minus x minus 9 over x times x minus 3 all squared. So for this, we notice that we have two linear factors, x and x minus 3, with x minus 3 appearing with multiplicity 2. So our partial fraction decomposition in this case is going to take the form a over x, so that's the term corresponding to x in the denominator, plus, and because x minus 3 appears with multiplicity 2, we're going to have a term of the form b over x minus 3 plus a third term c over x minus 3 all squared. Okay, so our goal here is to rewrite our function that we had to integrate as a sum of these three functions for some constants a, b, and c, because integrating what we see on the right is going to be actually quite easy, especially in comparison to what we see on the left. Okay, so now we need to solve for a, b, and c, and to do that, well, we just combine what we see on the right by finding a common denominator. That's just going to be exactly what we find on the left. And what will we get? Well, we'll get the following. So we'll get what we see right here. All right, so common denominator was what we saw on the left, which is x times x minus 3 all squared. we multiplied this denominator by x minus 3 squared, so we had to multiply this numerator by x minus 3 squared. We multiplied this denominator by x times x minus 3, did the same with the numerator, and we multiplied this denominator by x, did the same with the numerator. Okay, well, the only way that this can be true is if the two numerators are the same, because in fact the two denominators are the same. So let's write that down. So this is true if and only if 2x squared minus x minus 9 is equal to a times x minus 3 all squared plus b x times x minus 3 plus c times x. Okay, so we're looking to solve for a, b, and c such that this is true. Now, this is going to have to be true for all values of x, and so it's going to be true for any particular value of x. So we're going to try to use the method where we pick various values of x, evaluate the left-hand side, then evaluate the right-hand side, equate them, and use that method to solve for a, b, and c. As we showed in class, another way to do this would be to expand the right-hand side and write the right-hand side as a particular constant times x squared plus another constant times x plus another constant, equate the coefficients, and solve for a, b, and c in that way. In this case, I'm going to pick points. Okay, so we'll try to pick our points strategically. So to start, let's pick x equal to 0, because when x is 0, these two terms are going to disappear. So what do we get when x is equal to 0? We get, on the left-hand side, minus 9 is equal to a times 0 minus 3 all squared is minus 3 squared, which is 9. So times 9 plus b times 0 is 0. Plus c times 0 is 0. So that's just equal to 9 times a. So minus 9 is 9 times a. That tells us that a is equal to minus 1. All right, so we've now solved for a. That's good. Let's pick another point. So another good choice of points is x equal to 3, because when x is 3, this term will become 0, and this term will become 0. Okay, so taking x equal to 3 now, as we said. On the left-hand side, what are we going to get? So we're going to get 2 times minus 3 squared, that's 18, minus 3 is 15, and minus 9 now is equal to 6. So we'll have 6 is equal to, when x is 3, our first term with a becomes 0, our second term with b becomes 0, and we have 3 times c, and so 3c is equal to 6, which implies that 6 is equal to, c rather, is just equal to 2. So now at this point, if we want to pick a third value of x, we notice that we've actually picked all values of x where the right-hand side of this equation here becomes, where parts of the right-hand side of this equation here become 0. So the only places where parts of this right-hand side become 0 are when x is equal to 0 and when x equals 3. So I'll have to pick another value which maybe isn't quite as good, but because we've already solved for a and we've already solved for c, we'll be just fine. So what am I going to pick? I'm going to try and pick a number, x, which will not make our numbers too large. So in particular, I'm thinking to pick x equal to 2, because then 2 itself is a fairly small number, and 2 minus 3 is just going to be minus 1, and minus 1 is definitely going to be easy to deal with. Okay, so we'll take x now equal to 2. And evaluating the left side up here, what are we going to get? So we're going to get 2 times 2 squared is 2 times 4, that's 8. Minus 2 is 6, and minus 9 is minus 3. So we'll have minus 3 on the left, and what are we going to have on the right? So we're going to have a times 2 minus 3. So I'm looking right here. A times 2 minus 3. 2 minus 3 is minus 1. Square that, we get 1. So we get a times 1. And a, we already know, is minus 1. So this is minus 1 times 1 plus b times, so coming up here again, we're going to have 2 times 2 minus 1 is 2 times minus 1. Let's write it as 2 times minus 1, and plus the c times 2, that's our last term. We already know that c is equal to 2, so we're going to have 2 times 2, which is 4. All right, well, this means that minus 3 is equal to minus 1 plus 4, which is equal to 3. And we're going to have minus 2b. And what's this equal to? This means that 2b is equal to 3 plus 3 is 6, which implies that b is equal to 3. Okay, so we've now solved for A, C, and B. So that's good. All right, so we've now solved for, as we said, A, C, and B. So coming back up here, we know that the function here that we wanted to integrate, we knew that we could write it as a over x plus b over x minus 3 plus c over x minus 3 squared, and we now know that what a, b, and c are, so let's just write this down with a, b, and c as we found them. So our original integral I was 2x squared minus x minus 9 all over x times x minus 3 all squared. And this was equal to a over x, where a we saw is minus 1, so we're going to have minus 1 over x plus b over x minus 3. B we found was 3, plus c, which we found is 2 over x minus 3, all squared. And so we just have to find the integral of this function that we see here. And that is not going to be too hard. So what do we have? Well, the integral of minus 1 over x is minus log absolute value of x plus 3. The integral of 1 over x minus 3 is log absolute value of x minus 3. Differentiate that if you like, and you'll see that you'll get 3 times 1 over x minus 3 as needed, plus, and let's pull the 2 out of this, and let's just take a moment and look at the integral of 1 over x minus 3 squared, which we could write as x minus 3 to the minus 2 dx. Now, for integrating this, if you want, you could let u equal x minus 3, and du is then going to become dx, and your integral is just going to become u to the minus 2 du, which we can easily integrate. I'm just going to, at this point in the class, see if we can do this without actually doing this little u substitution. We can. It's going to be, so rewriting what we have already. And I'm going to treat the integral of x minus 3 to the minus 2 just as I would treat the integral of u to the minus 2. and then we check afterwards to see if it worked. So plus 2, what would I do? I'm going to add 1 to my original power here, which is going to become minus 1, multiplied by the reciprocal, in other words, multiplied by minus 1, and check if you were to differentiate this, minus 1x minus 3 to the minus 1, you'll get minus 1 times the minus 1 will come down and cancel, and you will get x minus 3 to the minus 2 as needed. Of course, there's nothing wrong with doing that u substitution. That's fine. Okay, so we're now done. But maybe I just want to rewrite this last one. Last term here as minus 2 over x minus 3, and this plus c, and now we're done. Okay, so that's it. What do we need to remember? Well, as before, you see an integral like this one here. It's a rational function. Degree of the denominator was less than the degree of the numerator. No division, therefore, was necessary, and we could apply the method of partial fractions immediately. That just involves factoring the denominator as much as possible, as we did here, and knowing what the corresponding partial fraction decomposition was going to look like this, then solving for a, b, and c as shown below and as shown in class.